So I welcome everyone to this session of the Midwest Computability Seminar. Very happy to have two talks today. The first one given by Vittorio Cipriani, who'll be talking about the Cantor-Bendixson theorem in the Weihrauch lattice. Thank you.
Okay, thanks a lot for the introduction, and thanks a lot for inviting me to this session of talks. And today, as you can read from the title, I will speak about the Cantor-Bendixson theorem in the Weihrauch lattice, and this is a joint work with Alberto Marcone and Mario Valenti. So to start, in this framework, actually, we are using Weihrauch reducibility, and we want to consider a classical theorem from the descriptive set theory. That is the Cantor-Bendixson theorem that states that every closed set X of a polyspace can be uniquely decomposed in the disjoint union of some big set that is the largest perfect set that we can get, and we know that it exists, and an accountable set. So we will denote actually the largest perfect subset of X as the perfect kernel of X, and this is usual terminology. And what is left in the closed set, we will actually call it the scattered part of the set. So the countable set is the scattered part. And now it is like, we know that actually many times theorems comes in a pi1 form, namely a form something like the form for all x in X, if some property phi of X holds, then there exists a Y such that the property psi of XY holds. And actually, this can be really naturally translated as a computational problem, and namely an input-output problem, in which, for example, we want an input, an X, such that phi of X hold, and we want to produce an output, because there is possibly more than one that is suitable for our input X, such that psi of XY holds. And notice that actually we will show that for many theorems, there may be more than one natural way to phrase it as a computational problem. So to study the computability on a generic space X, we would like to transfer what we know from computability in the burst space into space X. So that's why we want to encode every element of X with some element of the burst space. And that's where comes the definition, what is a representative space? That is a pair that is given by the set X and a possibly partial surjection that goes from the burst space into X. And if I have that delta X of P is actually equal to X, I will say that P is a name for X. So before I said computational problem, but actually like a computational problem can be seen as in computable analysis is usually called a multivariate function, namely a function that goes from represented spaces to represented spaces. And the two arrows denote that indeed that they possibly be multivariate. And so now that you have the notion of what is a problem in Weihrauch terms, we can state what is Weihrauch reducibility. So we have f and g that are possibly partial multivariate function on represented spaces. And we say that f is Weihrauch reducible to g if actually there are two computable functional that are phi and c that are single valued, such that if you give me an input name P for the input X in the domain of F, now what is usually called the forward functional phi, like computably transform a name for F into a name for an input of G. And with this now we can use G. And using G and the initial input, using a name for resolution of G and the initial input, we actually want to produce via the psi that is usually called the backward functional, a name for a solution of f of X. So in reverse mathematics, actually, there's a nice interplay between reverse mathematics and Weihrauch reducibility, in which in reverse mathematics we have the so-called big five phenomenon, in which most of classical theory of reverse mathematics actually goes into this big five subsystem of second-order arithmetic. And actually, most of the work have been done in the first three levels of the Weihrauch lattice. So there are natural candidates in the Weihrauch lattice for these subsystems. But in this talk, actually, we will work a bit more at the highest levels of the Weihrauch lattice. Actually, for pi1CA, that is the subsystem in which we will focus today, the situation is quite clear, because translating in Weihrauch terms, a principle in reverse mathematics is equivalent to pi power 1 Ca naught, actually we have the natural candidate that is the parallelization. I will explain in a moment what the parallelization is of the characteristic function of a pi power 1 complete set. So when I say the parallelization, simply think of, I have a problem f, I have countably many f that I can use, and you give me an input a countable sequence of instances of f, and I want to solve all of them, but I will solve all of them in parallel. So there is no interplay between solution of f. And actually, so far, like for it or not, the situation is a bit different, even if we will not see it here actually in this talk. Namely, we have many candidates of different strength, and indeed you can, like, just to mention two candidates that will be useful for the next of the talk. Actually, we have the choice on the Baire space that can be stated as you give me an input, an ill-founded tree, and I want a path for that tree. Actually, with ill-founded, it simply means that there's a path in the body of the T. There's an infinite path in T. And you see there is its restriction, but we're restricted to trees that have a unique path. So now, like, as I said, the Cantor-Bendixson theorem mainly wants two components as output. That is the perfect kernel, is the largest perfect subtree of a closed set, and the scattered part, that is a countable closed set. That is a countable set, sorry, not closed. And how do we phrase it in Weihrauch terms? Well, before let's say I want only one of the two outputs. So I can say, you give me, like, here we will stay with X, where X is a computable complete metric space that actually somehow is the translation of what is a Pauli space in descriptive set theory to what is a Pauli space where computability comes into. So the perfect kernel X, PKX, is the principle that given an input a closed set of in the space X, I want as output its perfect kernel, whatever its representation is, we will see it later. The perfect kernel tree actually wants an input a tree T and want the largest perfect subtree of T as a prune tree, named so as a prune tree in which there are no dead extensions. I mean, there are no nodes that do not have a successor in the tree. And otherwise, I can ask only for the scattered part, namely the countable part. So you will give me an input as a closed set in the space X, and the first list we will notice is the so-called, let's call it weak list. That's why the W, that actually outputs a list of the perfect kernel of the elements outside of the perfect kernel, but every of these elements have a bit at the beginning, such that if this bit is 1, then it is an element. It is a real element of the scattered part. Actually, we could have repetition. We could have garbage elements, namely that have the bit bi equal to 0. But actually, we know that the list will be complete. So it will list all the elements in the scattered part. The strong list, actually, so scattered list without a W, is the same as weak list, except that we want an injective list actually of all the paths that I have in the scattered part, but I want also the cardinality of the scattered part. So I will code somehow if it has countably many, if it is infinitely many paths in the scattered part, if there are only finitely many, and if there are finite, how many are there. And we will see actually later that this is this cardinality that really makes this principle, like, just to spoil that the scattered principle is stronger than the weak scattered one. So the first lemma, like that, the first theorem that was actually shown by her in this area of pi power 1 Ca and Baire reducibility was shown by Ernst. It actually showed that the perfect kernel for trees is actually equivalent to the parallelization of the characteristic function of pi power 1 complete set. And notice that this is completely in line with what happens in reverse mathematics, for example. So now, let's take some simple properties of the perfect kernel theorem, and namely notice that the perfect kernel theorem is equivalent if we consider trees in the Cantor space or in trees in sequence of 0 and 1s, or if we see in trees on natural numbers. And the same holds for closed set. So the perfect kernel principle is exactly the same if we consider closed set of the Cantor space or of the Baire space. Actually, it can be easily seen that this principle is parallelizable, that its parallelization is equivalent to the problem itself, because you simply take the tree and you join all these countably many trees that you have in a new tree. Then, if you want the end instance output of the end input of the sequence, you simply search for the tree that starts with n, and you will find the perfect kernel of that specific tree. Actually, to state let's say, the nicest property of what the perfect kernel principle is, we introduce this space that is the Sierpinski space. That actually is the space having only two elements, that is bottom and top, so for true and false. And the representation is simply like the only name that we have. So the only name that we have for bottom is 0 to the omega, so constantly many zeros. All the other names are valid names for the true. We will define a slightly different space, that is S pi 1 1, in which we have that the space in this space actually a sequence in the Baire space is a name for true if and only if P codes a pi 1 1 complete set. What does it mean? That actually, if it is true, like if it is not constantly 0 to the omega, my P, actually it will be a name for a pi 1 1 complete set. And I define with this name this map, even if sometimes in the literature it can be found as key S pi 1 1. Anyway, let's call it ID from pi 1 1 to sigma 0 1. And actually, with this, I want exactly to express that this function sends a closed set, a pi 1 1 set into a sigma 0 1. So basically, what this principle does is allow me to treat a pi 1 1 question as a computably enumerable question. And I will briefly show in the slides, like the proof that actually the perfect kernel in the Cantor space is actually equivalent to the infinite parallelization of this identity principle. So to show the first reduction, actually, notice first of all that, as always, I can code every closed set of the Cantor space with a tree, such that the body of the tree actually is the closed set A itself, and recall the collection of trees such that its body is countable is actually a pi 1 1 complete set. So countability is pi 1 1. And recall that in the previous slide, actually, we define ID like as a function that sends a pi 1 1 complete set into a sigma 0 1. And I have not done specification on what pi 1 1 complete set I want. And so, as PK counter is parallelizable, it is sufficient to show that a single instance of ID is actually reducible to PK counter. And well, we can easily show this because you give me an input at a tree in the Cantor space such that this ID principle says true, so something different from 0 to the omega, if and only if the body of T is countable. But actually, the body of T is uncountable if and only if there is no perfect subset in it, except for the empty set. So there is no non-empty perfect subset in it. So if the perfect kernel of T is empty. But actually, usually this will be, if we are, for example, in the Baire space, would be a sigma 1 question, but we are in the Cantor space. So well-foundedness of trees is a sigma 0 1 question, and we show the first reduction. So we just transform a pi 1 1 question into a sigma 0 1. Well, then if you give me an input to tree T, like for the reverse direction, if I want to show that the perfect kernel theorem can be solved with countably many instances in parallel of ID, first of all, we let T be the input, and with T sigma, the nodes that are comparable with sigma in T. So we start doing two things in parallel, computably. Namely, we start producing a copy S of our input, and for every node in T, we compute the identity on this T sigma I, such that, well, the identity is true if and only if T sigma I has a countable body. But then I will have like many answers. I will have countably many answers of this ID, namely every pi for T sigma I, and a name for a solution. Then recall that since the only name for bottom was 0 to the omega, if there exists an n such that PIN is different from 0, this means that actually the PI is coding a a countable set, a pi1 complete set. This is the set of trees that has countable body. And so what I will do, I will simply stop adding all the nodes that I have in T above sigma I. So in my S, I will start cutting all the nodes that are extension of sigma I. But since I'm doing this for every sigma that is in T, actually, we are removing from S all the infinite extension of the nodes that in T have countably many paths. So this actually happens to be a suitable name for the perfect kernel in T, because actually doesn't matter how long I go with the sigmas. Actually, sooner or later, if they have countably many paths below it, I will cut them, and so I'm recovering the perfect kernel of T. And just as a small corollary, like if we consider arithmetic Weihrauch reducibility, in which the phi and the psi actually are arithmetical instead of computable, we actually have that from the construction before. Actually, we simply need to answer a sigma 0, 1 question to countably many sigma 0, 1 question to arrive to the perfect kernel for trees. Actually, namely, what we were able to show is that the perfect kernel in the Cantor space is arithmetic Weihrauch equivalent to the infinite parallelization of key pi1, and the easiest way to see it is because perfect kernel is equivalent to the infinite parallelization of ID that transform a pi1 question into a sigma 0, 1. So anyway, like we want to consider other spaces X. So what happens if we turn to other computable complete metric spaces? Well, actually, if I have that for any basic open set that I have of X, that I have in my presentation, I would be able to show that actually the basic open set intersected with the closed set itself is countable. If I'm able to show that this is a pi1 property, then the previous proof just gives us that the perfect kernel of X is reducible to the parallelization of ID pi1 sigma 0, 1. And to do so, it comes in this lemma that, for example, is stated or in most classical descriptive set theory books, that in most of is actually stated a bit different, but we can get the following, that for every computable complete metric space X, so let's say effective polyspace, we have two things, that is a recursive surjection from the burst space into X and a closed set A, such that this surjection, if I restrict this surjection on the closed set A, actually this gives me a bijection with the space X that I started with. So what does it mean? That actually somehow, like doing some analysis of how, if we have a surjection, how behaves the maps in closed set, actually we were able to show that somehow the burst space is a kind of representative for is the most complicated one that we can get somehow for our principles. And indeed, remember that I already told you before that the perfect kernel counter is exactly equivalent to the perfect kernel in the burst space. And we know that in the burst space, asking for countability of something is a pi1 complete question. So what we get is that for every computable complete metric space X, actually the identity, the parallelization of the identity, or if you want the perfect kernel in the burst space or the perfect kernel in the Cantor space, they are all equivalent. They are above pkx. So this is thanks to the, let's say, this property of the burst space. On the other hand, we want also to know, like, the reverse direction. What happens, like, if I'm considering, what spaces X can compute, like, which spaces can compute the perfect kernel in the Cantor space? First of all, recall that if you are considering a principle like pkx, actually this we have to consider an X that at least can contain something that is perfect. It would not make sense to consider the perfect kernel on the natural numbers. Actually, it will be computable. It will always be like there's no perfect set. And so there's this notion of richness that for a computable metric space X, we call it rich, if actually there is a computable injective map from the Cantor space into X. We also know that actually it can be proven by Brodka and Gherardi that also the I-1, so the partial inverse, is actually computable. So what we have is that if X is a complete rich space, actually I have this computable injective map, then also the converse, like also the converse on closed sets is true. So I have that perfect kernel Cantor space reduces to pkx. And as a corollary, we get that actually for all interesting space, let's say perfect kernel and perfect kernel in a Cantor and perfect kernel in a space X coincide. So now we want to start with the full Cantor-Bendixson theorem. So we have the full Cantor-Bendixson theorem, we can state it for trees. Full, I mean that you give me an input a tree T or a closed set, and well, I want both the perfect kernel and a weak list, where weak, recall, that means that there is no cardinality. We are missing the information of the cardinality in the scattered part, of the elements in the scattered part. Or we can say, yeah, I want also the cardinality, so I want also a strong list. Actually, we were able to show that the weak list is strictly below scattered list, that is strictly below the parallelization of key pi 1, 1. And since key pi 1, 1 is trivially parallelizable and can compute all of this, well, actually, as a corollary, we immediately get that all these principles are equivalent. But if we are considering closed sets, so these are the same principle but stated for closed sets, actually what we get is that we were able to show with a similar proof technique of the one I gave above. Actually, there are some details to adjust, but we can make it that the weak scattered list principle in the burst space is actually equivalent to the perfect kernel in the Cantor space. So recall this lemma of that actually we have a surjection and we have a closed set in the burst space, such that the surjection restricted to that space give me a rejection of my X, of my space X. And so as a corollary from this, we get that both for weak list and for scattered list, the list in the bare space is the most complicated we can get if X is a computable complete metric space. Doing so, we actually immediately reached that weak list was equivalent to pk Cantor and was equivalent to pkx, and pk Cantor is parallelizable. So in parallel, we compute from one side the perfect kernel, from one side the scattered list, and we get that for all spaces X, I mean, that makes sense to consider the Cantor-Bendixson theorem. Weak Cantor-Bendixson X is actually equivalent to pk Cantor, the perfect kernel in the Cantor space. So now, like, recall that actually the weak scattered list was equivalent to pk Cantor, but below the scattered list in the bare space. So we cannot hope to have a straightforward result like this one for CB. So recall that X is a computable K-sigma space if actually X is a computable magic space, and there is a computable sequences of non-empty compact set, computably compact set actually, such that this the union of this computably compact set is exactly X. Well, for this, we were able to show that actually even CBX Cantor-Bendixson theorem for X is equivalent to the perfect kernel in the Cantor space. And very informally, like the only information that is missing is, as I said, is the cardinality of the scattered part. But actually, we were able to show from one side, we compute with the weak Cantor-Bendixson theorem, the weak Cantor-Bendixson principle for a space X. From the other side, pk Cantor is able actually to compute along the scattered part of a K-sigma space. So then from the cardinality and a weak list of the scattered part, we can actually computably recover a strong one. So like now, right now I'm coming to the conclusion that unfortunately for the Cantor-Bendixson theorem in a space X, with X that is not K-sigma, the situation is not so clear as it is, because we have this theorem of Hurewicz that tells us that if X is a polyspace, no effectiveness here, then there is an embedding of the bare space into X such that its range is closed if and only if X is not K-sigma. So, but actually, as I said, this theorem is really not effective. And so actually the only thing that we could get is actually the following, that if you give me an input X as a polyspace that is not K-sigma, then we have an oracle that tells us that that the Cantor-Bendixson theorem in the space X is actually not K-sigma, is actually equivalent to Cantor-Bendixson in the bare space relatively to the oracle. So coming to the conclusion, like we have analyzed like this principle, and like we have this degree in which there are really many things like PKX, the weak scattered list in the Baire space, the weak Cantor-Bendixson theorem, and also the Cantor-Bendixson theorem for spaces that are K-sigma. Strictly above, we have with the scattered list principle, actually strictly because scattered list is able to compute actually the characteristic function of a single pi11 set, actually a bit more, but actually, so anyway stronger. We don't know if this reduction is actually strict or not, but we have that CBX is for, like, here I'm cheating a bit actually. CBX here holds for relatively to an oracle. So think to this degree where if you want to consider that, we have CB Baire as a representative. Anyway, stronger than the scattered list. Above everything, we have the world of the trees and of the parallelization of pi11 complete sets. And just to state what was already known in the Weihrauch lattice, we have that UC Baire actually is strictly below the perfect kernel principles. It happens that the perfect kernel and the choice on the Baire space are actually incomparable. And but if we restrict to arithmetic Weihrauch reducibility, what we get is that all of these principles collapse in a single degree. And like now I'm really finishing the talk, like just mentioning that actually most of the proof, the separation we have in the previous one comes from the characterization of the first order part of a problem that was introduced by Zapparo, Solomon, Yokoyama, and is the hardest problem with codomain n that F can compute. Also, like, consider this operator that was introduced by Soldai and Giovanni that will, in the next slide, will become clear what it is. It's like a generalization of the parallelization operator, but informally, we can solve unboundedly many instances. So not only finitely many instances of them. And so characterizing the first order part, actually the first order part are equivalent to the first order part of the unique choice on the Baire space. Is equivalent to pi11 Cn. Now simply you give me an input a sequence of 3 of which one is well founded and you give me an index of that. Is equivalent to the restriction on unique choice. So it is sigma 11 and delta 11. Is equivalent to all the unbounded star parallelization of the principles above. So unboundedly many, but finitely many. To the unbounded parallelization of ID. So all these equivalents allowed us to say that actually the perfect kernel, the first order part of the perfect kernel principle, and is strictly below the first order part of C Baire, is strictly below the first order part of pi11 parallelized. And indeed, we can show that the parallelization of pi11 Cn and UC Baire, if you parallelize, that is strictly below sigma 1 Cn parallelized, and is strictly below the implicit parallelization of pi11. So that's the last slide of my talk, and thanks everybody for your attention. Thanks everyone for your attention, and if you have a question, please.
Thank you. Let's thank Vittorio.